All right, as everyone's logging on, I want to say hello, good morning, and welcome to today's webinar. This webinar is titled The Importance of Optimizing Cooling with Smartflow. My name is Mark Zaborny. I am the marketing manager over here at DME, and I'm so excited to have you join us today for the DME webinar series. Before we begin, I want, and while everyone's still logging in, just a few quick housekeeping notes. If you haven't already, please follow us on LinkedIn and on our YouTube page to stay updated on all the latest things that we have going on here at DME. And you can also check out our amazing products that we have at the DME e-store. You can register there, have your account there, so you can purchase online 24/7. The links for all of this will be posted over in the chat. Also, you could access any of the past and future webinars that we're going to have. You can register for those over at dme.net/webinar. That's dme.net/webinar, singular, no S. Also, at the end of this webinar, we value your input, and we have a survey for you, a quick 2-minute survey that is going to be more about the future of our webinar series and what you would like to hear from. So if you can take time to fill that out, that would be much appreciated. But for today, it's my pleasure to introduce our expert speaker. We have Corey Brown, the president of Smartflow and Berger & Brown Engineering. Corey brings decades of experience in thermal management and will walk us through how optimizing mold cooling can dramatically improve efficiency and product quality. Please feel free to submit your questions in the chat at any time, and we will answer them at the end of the presentation. After the webinar, an email will be sent out to all the attendees with the recording, the slides, all of the handouts that are also on in here as well, and any links that we have as well. Again, thank you for joining us, and let's get started. Corey?
Yeah, good morning. Mark, thank you for your time, and the DME team. Thank you for allowing me the opportunity to present. And thank you for everybody else that's on the call, and hopefully we can enlighten some people and provide some guidance. So as Mark said, I'm president and CEO of Berger & Brown Engineering. Berger & Brown Engineering has been around since 1978. We are the designers and manufacturers of the product line Smartflow, which supports the injection molding industry, primarily based on the cooling side of the process. So today we'll kind of talk about the importance of injection mold cooling, and how do we optimize our processes to ensure we've got effective cooling and ultimately good parts in the end. So the cooling process usually makes up about 60 to 80% of your total molding cycle time. So the cooling process is very important to be optimized and be efficient, to be able to help make good parts and to reduce your cycle time. So first, we'll kind of start talking about the state of water, which is critical for cooling, and that is what we call turbulent flow. Turbulence is equal to process stability and optimum cooling. And turbulence is what I like to call just the state of the water as it is flowing through the circuits. You can either have laminar flow or turbulent flow. And there's a calculation that you calculate, it's called the Reynolds number. And anything above 4,000 for a Reynolds number is considered to be in turbulent flow. And anything above 8,000 is what we consider kind of the point of diminishing returns. So the sweet spot for the state of the water for optimal cooling is between 4,000 and 8,000 Reynolds number. So we have this chart here showing steel temperature versus flow. So in this situation, it's a 3/8 inch diameter cooling line with 70-degree cooling water. And you can see up to a half GPM on the left-hand side here. You can see that minor changes in flow make a large difference in the steel temperature, meaning the minor changes that we add additional flow to get to that turbulence, you can see the additional extreme changes in the steel temperature. But once you get past 4,000's Reynolds number, it becomes more of a steady change, less aggressive change as flow increases. And then above 8,000, you can see it's very minimal, the steel temperature change for additional flow. So after that 4,000 is where we get into that turbulent range, and that's where we're going to get into the most optimal cooling. So you can see on the left-hand side, before turbulent flow, we have what we call unstable steel temperature. And then once we get into the Reynolds number of 4,000 and turbulent flow, we have stable and efficient steel. And then above 8,000 is what we consider wasted capacity, because the more you add flow, which is just energy, water capacity, it makes little difference on the steel temperature at that point. So we've developed this turbulent flow calculator. It's free for everybody to use, but you can use this on our website, and you can go in and do simulations for different areas. So we'll just do a quick simulation. So, you know, the one we talked about here a second ago was 70-degree water, 3/8 inch diameter. So let's just do 60-degree water, and then we'll do a 1/4 inch, so 0.438 on the tap chart. And then we were not going to add glycol right now, and we're going to say we want a 4,000's Reynolds number. So in order to get to turbulent flow at 60 degrees Fahrenheit through a 1/4 inch port, we need 0.64 GPM. Let's go 8,000, so we'll go to the top end. We need 1.29. So this would be the optimal cooling flow through that 1/4 inch circuit to achieve turbulent flow and the optimal cooling. Now, one of the kind of inhibitors to cooling is your water chemistry. And a lot of people in the industry use ethylene glycol. So I'm going to show you kind of the difference between no ethylene and adding some ethylene. I think 30% is pretty common in the industry. So all things stay the same. We went from 30% or from 0% ethylene glycol to 30%, and we had to go all the way up to 2.76 GPM versus the 1.29. So more than double the flow rate to get to turbulent flow, to get to the optimal cooling range. The viscosity increases by adding ethylene glycol. So as a result, it takes more flow to get the water to turbulent flow by adding ethylene glycol. So that's a common trend is what we just want it to be colder to be more efficient. But as a result, you have to pump more water to be able to get to that same heat pull if you were to just have 0 ethylene glycol. Now let's talk about water temperature, which is another contributing factor to the Reynolds number. Let's go to 100 degrees. So at 100 degrees, all we need is 0.79 GPM or 0.8 GPM to be able to get to that 8,000's Reynolds number. Where the colder the water, we now have to almost double that to get, or not double that, but 60%, 70% higher to get to the 1.3. So you're still going to get the optimal cooling at that 100 degrees as you would at 60, but you have to pump more water through at the 60 just to due to the water chemistry of the water. I like this diagram down here to the right that kind of shows you the difference between turbulent flow and laminar flow. So in laminar flow, the water is moving through the circuit in a consistent way. So as a result, the only portion of the flow that is going to get the heat transfer is that outside section of the water. The inside and the middle aren't going to get much heat transfer. But in turbulent flow, because the water has eddy currents, has whirlpools, has vortices, all of it is going to contribute to the heat transfer. And that's why we get optimal cooling in the turbulent flow, because that's going to be the most efficient way to cool the circuit. I'll go back to the presentation here. So we're going to show this a video here about balancing. So as most of you know, water is going to take the path of least resistance. So another inhibitor to optimal cooling is an unbalanced tool. Now, this is all things considered, hoping that the design is correct and we've taken care of good practices when designing the tool. All things considered, you know, a balanced tool is going to create that optimal cooling. So if we have an unbalanced tool, you're going to create hot spots, you're going to create sag, you're going to create droop, you know, all big issues when it comes to creating conforming parts. So we're going to watch that video real quick. And what we're showing here is we are showing a simulation of a tool. And I'll pause it a few times throughout the video. So right now we have 3 circuits going through this tool. And what we've done is we've calculated that we've got one circuit that's got 15,000 Reynolds number, we've got one circuit that's got 4,000, and one circuit's got 1,000. You know, likely this top circuit is maybe a straight through circuit. Maybe this 4,000 has a tortuous path, meaning it has a lot of areas that it has to go around, corners. Maybe that third circuit's a bubbler. So the water is going to take that path of least resistance through that first circuit. As a result, the Reynolds number is going to be higher because it's getting the majority of the flow. So now that we know what we have in that circuit, so we have the vision with the flow meters, we can see what's there. So then what we can do is we can add regulators, and we're going to dial back that first circuit to get to that 6,000, that sweet spot between the 4 and 8 on that first circuit. And as a result, it's pushing water to the next circuits. So we went from a 4,000 to a 9,000 and 1,000 to 3,000. So then what we can do is then we can dial back the second circuit to get to that sweet spot 6,000, and it's going to force the additional water to that third circuit. So now we have optimal cooling through all circuits, and that's a balanced and optimized tool at that point. So that is critical for having a optimal cooling, is to have a balanced tool. So we're going to go through a case study. We had a customer that came to us and said they've got a product that they are manufacturing, and it was a grill for an automobile. And they had 16 zones. Each circuit was 3/8 inch, and then they were feeding 90-degree Fahrenheit water to the tool. We asked them, hey, what flow do you guys have through the circuit? Do you guys have turbulent flow? Where are you at? And they had no idea. So we sent them some flow meters and regulators, and they were able to find that 5 of the 16 zones had 0 flow. And some of the zones were flowing at 2.5 GPM. So as a result, you know, you've got 5 zones out of the 16 that now have hot spots, aren't getting the effective cooling, and they're just going to remain hot and not cool during that cycle. So we worked with them on the turbulent flow calculator, put in the 90-degree F. I think they were running 10% glycol. And what we found is that they needed 0.66 GPM to get to the 6,000 Reynolds, or 4,000 Reynolds number, I apologize. So what they did is they added regulators, and they went through and balanced it, and they made sure that the areas where they had known hot spots and they were having major issues, they made sure that they had excessive water going through those. So they regulated it back to make sure that they had 1.5 GPM known in those hotspot zones, and then at least 1 GPM through all of their circuits. And what the measurable results were is before they had a center droop of 1 millimeter and greater, a parting line delta T of 20 to 30 degrees Fahrenheit, and they were also using 3 thermolators for cooling. Afterwards, they were able to reduce the droop to 0.4 millimeter max, so they were able to take 60% off. They were also able to take 10 degrees off the delta T parting line temperature. And then they were also able to reduce from 3 thermolators to 2 thermolators because they balanced it and they saved water capacity for their other zones. So that just kind of goes to show how effective cooling can help and greatly improve one processes and part quality. Another inhibitor to cooling is scaling. So we have a slide here, and I'll come back to this. It shows, here we go. So 5/10 of scale, or sorry, 5/100ths of scale, so 50 thou, is equal to about 3 to 5 inches of additional steel added to that tool. So the quick and easy I like to say is 10 thou of scale is equal to 1 inch of steel. So scale is a huge inhibitor to optimal cooling. So the more scale you have, the more cooling you're going to have to be able to correct or overreact to that scaling that's on there, which is like adding an additional 1 inch of steel between the circuit and the part face. So being able to bench line your tools when they first come in with pressure and flow to determine what the flow rate and the pressure rate is through that circuit, so that in 6 months or a year, you can bring them back in and you can check them again for the same flow rate. If your pressure increases, you're likely going to have scaling, which is going to be a huge inhibitor to the optimal cooling that you're looking for. So to kind of go back around, your cooling cycle is anywhere from 60 to 80% of your total molding cycle. So optimal cooling is critical to be able to reduce that, create good part quality. Some of the inhibitors to the cooling are design, which it's very critical for the designers of the tools to understand turbulent flow, to make sure that they can design the cooling circuits correctly and optimally, to make sure that we have the good parts in the end and set us up for the best manufacturing ability process. Other inhibitors are blockage, so any scaling, any blocks, any rust, anything that goes into the circuit, and then also the flow rate. So if we're not getting optimal flow and optimal water characteristics, then that's going to be a big inhibitor to optimal cooling. So there's a couple tools on our website. Let me go back to that. So on our website, we've created under resources, we have both a turbulent flow calculator and a scientific cooling calculator. These are both free resources on our website for you and your team to be able to go in and do the calculations on your zones and just make sure that you're in the optimal cooling range. The other thing is the scientific cooling calculator. So if you want to determine the amount of heat transfer and the amount of energy that you're going to need to pull to be able to effectively cool, you can go in and put variables in here, and it'll give you your potential delta T's and your flow rate and your inches that are required to be able to effectively cool as well. And then we also, I think Mark mentioned it, we put some resources into the chat, and you can access those. We've got a setup sheet in the chat. We also have a magnet, a picture of one of our magnets that we always send out, and it has kind of the basics of turbulent flow for certain circuit diameters and temperatures. Real easy, quick and easy chart to look at and to reference when you're on the floor, and helping that team get to the optimal cooling. That is all I have for today, and I appreciate your time, and I think Mark will open it up to questions. Is that correct?
Yes, thank you so much for this right now. And everybody on the chat, if you do have questions, please put them into the chat and we will get to them right now. First question we do have is a simple one. Can we get a copy of this presentation? Yes, as soon as this, this is over, where I'm going to send out an email out to all attendees of the webinar, the recording, the slides, and all the handouts as well, just in case you guys missed them. We do have some other questions coming in right now too, Corey, for you.
Yep.
First question is, does it matter if the flow regulators are on the supply or return manifold?
Yes, it is critical to have regulators on the return, because if you have, you're blocking the flow, regulating the flow on the return, so you know for sure you have that same amount of flow going all the way through the circuits at that point. Where if you have it on the supply, you potentially won't have the back pressure and you're not going to have full port flow potentially through the circuits.
Okay, great. And then the second question is, how does pressure affect the flow rates?
So pressure is going to push more flow through a given diameter. So if you need more flow through a circuit because you've got blockage or you've just got a tumultuous path, you're obviously going to have to increase your pressure to get more flow through there from a pumping standpoint.
Okay. And again, if anybody has questions, let's put them into the chat and we will get to them. Let's see, how much efficiency to process? Some message you got in there.
I guess, can we clarify that question?
Yeah, if you could help us out with that one. Next question while we're waiting for that one is, how do you benchmark a tool?
Yeah, so the common practice that we've seen and that we kind of teach is when you first get a tool from the tool builder or into your facility, we put it up on the bench in the tool room, and we have a separate pump and flow meter and regulator that we utilize. What we'll do is we put the flow meter and the regulator on the return side, and we put the pressure gauge on the supply side, and we will get to a known flow rate, let's just say 2.5 GPM through that circuit, and we'll check the pressure. So we'll record the pressure at that time. We'll do that for every circuit. We document that, we save that. So 6 months, let's just say, hey, the tool doesn't seem to be operating as well as it was. Let's take it off, let's look at it. We will do the same process. We will go to the same flow rate, so the 2.5 GPM theoretically, and then we'll check the pressure. And if pressure is the same, that means that all things have stayed the same. We likely don't have any scale. But if pressure is increasing, that means that we've got a restriction of some sort through that circuit. It's because we're having to push with more pressure to get that same flow rate. So likelihood was we have a blockage, we've got scale, we've got something going on. And that's how we would suggest benchmarking the tool and then doing the checks, every 6 months, every year.
Okay. Let's see, a follow-up for this one is, can you incorporate this with an existing system? I think.
Yeah, I mean, if you have a tool already in process, and let's just say you just have a manifold and you're just running the lines to the tool, yes, you can use quick connects and jump in. We always suggest take a quick connect, put a flow meter in there, and go from circuit to circuit to circuit and just see what you actually have. And that at least will give you the vision and give you the understanding of currently what are you running at.
Okay. We have a question about scale.
Yep.
Would it be best to have the supply water softened or perhaps reverse osmosis water to give a much better quality of water in the first instance?
Yeah, I mean, anything you can do to give yourself the best opportunity to prevent scaling, yes. But then, adding chemicals and having the water treated is always good, but then you also don't want to go too far either, because then that's going to cause potential issues with pumps and seals. So it's just finding a good balance. But yes, you definitely want to have your water treated and maintained, because the other thing too is as you if you're using a cooling tower and some of that water is being evacuated through air or steam or just natural, all that sediment and those minerals are going to stay in that water, so your concentration is going to get higher and it's going to eventually collect somewhere. So yes, I mean, treating your water is best, but it still has to be maintained as well.
Good advice there. Again, if you guys have questions, please put them into the chat. Another question we have is, what is the maximum temperature that your flow meters can handle?
Standard is 250 on the electronics, 250 Fahrenheit. And then on some of our high temp flow meters, we can get up to, I believe, 400 F.
Okay. Great. Is there a universal target difference in the water temperature for supply and return waste or return water?
No, I think you're going to have, it's all dependent upon how long your path is, what temperature you're operating the tool at, what are you adding the cooling water at, it's all going to change from tool to tool to tool. So it's best to kind of do the calculations, try and get a benchmark of what you think it should be, and then go from there.
Okay. All right, so we have someone here, they want to know if you have any flow meters for hot oil. Currently they're running at 300 F, and I guess those flow meters are digital.
Yes, we have mechanical, but we don't have digital.
Okay, another question we have, to follow up on that one is, will you be giving digital in the future?
We're working on it. We are working on high temp for water right now, and then if potentially maybe for oil in the future.
Okay. For descaling, or they're currently using glycol. Would that be useful?
For descaling?
Yeah, descaling.
Like I said, it depends on the water's chemistry. I mean, glycol is going to help kind of keep the water chemistry down, but it's a cooling inhibitor, let's put it that way, because of the viscosity. So yeah, glycol helps with kind of putting a coating on the steel and in the lines, but at the other side of that too is it's an inhibitor as well.
Okay. Great. I guess last call for questions for Corey. If you have anything right now, we hit all the questions so far. So I'll just want to give everyone out at that end.
And we're more than happy to answer any questions if anybody wants to reach out directly, and we can answer and help and support all we can.
Absolutely. If you guys have anything, you can always call your DME rep or send an email through DME.net or the e-store, or call our customer service, and we'll be happy to assist you on that one. So last call for questions. And while we're waiting for that, Corey, I just want to thank you for taking the time today and sending this information over to us.
Yeah, no, I appreciate everybody's time and everybody that came on, and the DME team for allowing us to do this.
Absolutely. So yeah, looks like all the questions are done. So I want to thank everyone for joining us today for this webinar. We will be having another one probably mid-November because the holidays are coming in. So stay tuned for that. On that one, at the end of the webinar, there is a quick survey. I'd love to get your thoughts, just basically on our series that we had for the year on here. So love to have that. And other than that, we will be sending out an email with a recording of this, the slides, and all the handouts as well, probably later on in this week. So thank you so much for attending, and we will see you next month.